Hello, everyone. Thank you, Safa, for your nice introduction. And good morning and good afternoon to everyone. And welcome to my lecture. Today, I'm going to talk about a novel solar heat pump heating system and a number of key technology involved in this system. My name is Xudong Zhao, a director of Center for Sustainable Energy Technology, University of Hull. So my contact would include background information, technology description, thermodynamic performance, and the system demonstration. Briefly talk about CSET. Center for Sustainable Energy Technology is the recently established research cluster based at University of Hull, which is dedicated for research related to energy efficiency, renewable energy, sustainable heating and cooling, energy management, and green low energy building. We work on 6 themes in energy sectors, including renewable energy, energy efficiency, sustainable building service, smart energy system and storage, as well as distributed energy system. We currently have 24 people work in the center. So move back to the topic. We have won 2 million funding from a department for business, energy, and industry strategy to develop a low carbon heating system, which are applicable for public building. Of course, it could be applied to a domestic house. Project is led by University of Hull with MPS, PCM, and the Hull City Council. So talk about background. In the UK, it commit to reach carbon neutral by 2015, but current situation is most heating system is a high carbon intensive technology. Low carbon heating system only occupy less than 2% of the overall heating market. At the moment, gas boiler is dominate the heating market, and in the next 20 to 30 years, gas boiler should be quickly phase out the market, being replaced by low carbon heating technology like heat pump. It is predicted by 2030, around 2.5 million heat pump will be installed in new home in the UK. So talking about China, it is predicted China would reach peak carbon emission by 2030. However, Chinese government committed to reach carbon neutrality by 2016. So we got a big job to do in next 10, 20, 30 years to decarbonize heating system, make it carbon neutral. So talking about conventional solar heat pump technology, this technology will be applied in mid and high latitude climate application, has a number of inherent difficulty and challenge. First, solar collector have relatively low efficiency, and heat pump has a low COP during the winter operation. Contribution from the solar is quite limited because of low efficiency and mismatch between demand and supply. Particularly, frosting is a big issue. With defrosting heat pump take huge amount of electric energy. It is about 20% electric consumption being used for defrosting heat pump, which is a big energy loss. So talking about our technology, so to tackle challenge and difficult remain with current heating system, we developed a new solar heat pump heating system, which comprise primarily three major parts. Firstly is the multiple throughout flow solar panel array. We got panel, a number of panel, possibly 10, 20, which will be connected in a multiple through flow manner. This would allow fluid to go through the panel from the beginning to end, from the low part of the channel section. And then we got fluid move backward from upside section and then go forward from beginning to the end, make the several U-turn throughout the individual panel, throughout the panel array. We would be able to achieve relatively uniform temperature from beginning panel to the end panel, which can prevent overheat of the panel at the end side of the array. And in this way, we can prevent significant heat loss and increase overall solar efficiency of the panel array. Our simulation and experiment indicate if we have more than 10 panels connected in this way, we will be able to achieve around 20 to 30% higher solar efficiency. It is very effective. Cost remains same, but a different connection, different flowing in the panel array will recover significant amount of solar energy than the traditional one-to-one connection. Second technology is a double source heat pump with weapon ejection compressor. This kind of heat pump, we try to recover heat from both ventilation air, exhaust air, as well as ambient air. We have two evaporator connected in series. We got exhaust air pass across first evaporator, then we got exhaust air and ambient air mixed up and into second evaporator. By two-stage heat recovery, we can maximize heat recovery from the ventilation air. In the meantime, we make use of weapon ejection compressor, which can enhance the energy performance of the heat pump. By doing so, we would be able to achieve 30 to 15% increase in heat pump COP. This is the second part of our technologies. And the third part of technology is fast responsive heat storage and heat exchanger. If you look at this diagram, we got a tank. We have a tank separated into two parts. At the low part of the tank, we got very, very small volume space, maybe 20 liter or 30 liter. With this space, we got a heat exchanger embedded that allow heat transfer between solar loop fluid and heating loop fluid. Because of a small volume, this amount of fluid could be quickly heated in about 20 minutes. In morning, when solar rise and heat demand is critically required by the house, we can quickly deliver the heated fluid into the room space for heating. That's why we call it fast responsive. And during the daytime, we got more and more solar radiation, and heat demand from building is less and less. In this case, we try to alterate direction of the fluid and have this kind of low part fluid change flow direction and travel across the heat storage space, in which significant amount of heat will be stored in the storage tank and the remaining heat being delivered to the room space. So whenever in the afternoon or evening, solar radiation is less and not available. We got heat stored in the storage, being released and be delivered to room space for heating. In this way, we would be able to extend service time of the solar system and reduce operational time of a heat pump. That means we can significantly reduce electric consumption of the heat pump. We can maximize use solar energy, minimize use heat pump, which can save electric energy. This is three major parts of our system. So look at our heat pump. We got two evaporators. First, the evaporator going to recover heat from exhaust air, means discharge air from the room space. Afterward, we got exhaust air mixed with ambient air. This mixed air is then delivered into the second evaporator for further heat recovery. In this way, we would be able to maximize used ventilation air energy and minimize its energy loss. Most importantly, we can make use of exhaust air to defrost heat pump rather than instead of use electricity. We get rid of electricity, defrost heat pump, use ventilation air rather than electricity, achieve significant energy saving in heat pump defrosting. So this is structure of the heat pump. We got first evaporator, we got ambient air, exhaust air mixture, we got second evaporator, as well as weapon injection compressor. All combined together, we can make 30 to 15% higher COP. So this is a test rig for the double source weapon injection heat changer. We simulate room space, 20 degrees Celsius, hot water temperature, 35 degrees Celsius, ambient temperature, 0 degrees Celsius, and test its steady state performance and put it into the practical application. So look at this technology. We can say we make the first time effort to use weapon injection compressor for recover heat from ventilation air. And we make use of ventilation air to defrost heat pump rather than use electricity. Okay, compared to traditional exhaust air heat pump, which have a single stage evaporator and relatively small heat recovery volume and capacity, our new heat pump, because we have a two-stage evaporator and we got weapon injection practice in the heat pump, would be able to recover double heat energy from ventilation air. Look at the second part of second technology engaged with system. We got multiple solar panel and then connected in a multiple through flow way. For each single panel, we have it physically separated into 3 or 4, maybe 5 different flow channel. We have fluid pass across the low part of channel, then flow into the second panel, then third panel, finally to end panel of the array. Afterward, we have fluid flow backward from upside channel, then going upward, got the fluid flow forward from the beginning to end. By this way, we can effectively average temperature between the initial panel and the final panel in the array, which can prevent excessive heat loss in the final panel, because we can reduce temperature of the final panel and end panel. We can reduce heat loss of the final panel. As a result, overall solar thermal efficiency of the panel array is significantly higher than the traditional one-to-one connection manner. Our experiment indicate if we have 9 or 10 such a panel connected in multiple flow way, we would be able to achieve 20 to 30% increase in overall solar efficiency. So for each panel, we make use the microchannel structure. We got a corrugated geometry inside, which have a relatively small cross-section and lead to increase the fluid flow speed and increase the heat transfer between the channel wall and fluid inside. So lead to higher solar efficiency for individual panel. So this is a panel. We got multiple inlet, outlet, have the panel connected from beginning to end, from beginning to end, make the several U-turn, make the temperature uniformly distributed, prevent heat loss at end channel, and as a result, we can achieve higher overall solar efficiency. So this is an 8-panel established in the manufacturer of 5-star. We test the performance all side and then delivered to the UK to test the overall performance. So for this kind of layout, its a temperature profile would be something like this in the low left side. So at low part of panel, we got a relatively low temperature, and the high part of the panel, we got a relatively high temperature. In this way, we can prevent significant air convection heat loss, because we can prevent air convection around panel, prevent significant air convection loss. Another benefit, because we got fluid pass across panel horizontally without many U-turn, so only 2 or 3 U-turn, we can reduce the flow resistance and lead to increased EER, energy efficiency. So look at the third technology, fast responsive heat storage, heat exchanger. We got a tag, we got it separated into 2 parts. A low part, we got a small volume of fluid for heating, and also we got heat exchange embedded, enable heat transfer between solar loop fluid and heating fluid. So in this way, we will be able to quickly deliver heat to room space without much waiting, only 20 minutes. Whenever we got surplus heat, we got fluid change flow direction, transfer heat to storage, and then deliver the remaining heat to the room space. Whenever we got less radiation, we got stored heat released and to supply heating. In this way, we can extend the service time of solar system and minimize operational time of heat pump. So this is the control strategy of the fast responsive heat storage heat exchanger. So this is a storage tag. We got low part, got quite a number of connector that allow the heat exchanger to connect it to solar loop and the heating loop. So compared to traditional heat storage, heat change, which is slow responsible for heat demand, because you got quite a large volume, maybe 1 meter cubic and 2 meter cubic. Heating can be made available only we can heat up this amount of heat, which take about at least 3 or 4 hours. In that case, we need heat pump to switch or during morning time, got a significant electric consumption and less utilization of the solar energy. Our technology can overcome this difficult and challenge and make minimized use of heat pump. So talking about thermodynamic performance, so we test our new heat pump, comparing its performance with traditional vapor injection heat pump and air source heat pump. This diagram shows the correlation between COP and ambient temperature and COP and condensation temperature. You can say, compared to traditional air source heat pump, our heat pump can achieve around 23.2 higher COP, and at low ambient COP increase rate will be higher. Also, we look at the correlation between COP heat output and injection temperature. We can say at 5 degrees Celsius injection temperature and heat pump got maximal COP. There's an optimal. So in that case, we think vapor injection temperature should be about 5 degrees, which is optimal temperature. And we also analyze oxygen loss take place at a different part of the heat pump, including compression, evaporator, and condensation. We found oxygen loss, maximal oxygen loss take place in compressor, followed by condenser and low pressure evaporator, because we got 2 evaporators, one low pressure evaporator, one medium pressure evaporator. So look at injection temperature. We got, if we increase injection temperature, heat output will be decreased. So this is a general profile of the double source vapor injection heat pump. We can say increase ambient temperature and ventilation flow rate, COP of the heat pump will be increased. For our prototype, its COP will be in the range of 3 to 4.5, depending on its operational temperature. Compared to traditional air source heat pump, our heat pump achieved 30% higher COP at the same operational condition. So this is a heat output against ambient temperature, heat output against, as well as ventilation flow rate. This test and simulation indicate heat pump got heat output in the range of 6 to 11 kilowatt, and heat supply, we increase ambient temperature and ventilation air flow rate, the heat output would be increased. Look at defrosting. We can, for our technology, we make use of ventilation to defrost heat pump. Our defrost timing would be reduced to very, very short, only 10% of the total operation time at minus 5 degrees Celsius, where traditional heat pump got much longer defrost time, 20% operational time. That's why it uses significant electric energy for defrosting, which is a completely kind of energy loss. So this is a general comparison between our technology and existing heat pump, including conventional air source heat pump, exhaust air heat pump, and conventional vapor injection heat pump. In terms of power demand for defrosting, our technology got lowest power demand because we almost have no need for power for defrosting. We use ventilation energy. In terms of capital cost, our technology in the middle level in terms of per kilowatt heat output. In terms of operational cost, our technology got lowest figure because it doesn't use much energy. We use maximize use of solar energy and minimize use heat pump. And also our heat pump got highest COP. And we don't need much auxiliary heating requirement. So I got lowest requirement for auxiliary heating. So talking about solar panel array, we got 8 panel connected in this way. We tested performance at the inlet outlet temperature at different panel. We analyzed its performance. This is a test result during the daytime operation from morning to afternoon at different part of a panel. So you got panel 1, panel 2, panel 3, panel 4. On the right side, it showed the correlation between solar efficiency against the time with a different panel number. And our panel is 8 is efficiency variation during the daytime. Our test results show at operational temperature of 16 to 17 degrees Celsius, solar efficiency of the panel array achieve around 78%, which is higher than traditional one-to-one connected solar panel array. So EER of the solar panel array, left side show our EER and the right side show traditional solar panel EER. You can see you got significant increase in EER because the flow resistance reduced and over solar efficiency increased. So got increased heat output, decreased the pump electric consumption. So talking about storage tank, because of a small volume, we can quickly heat up the fluid in the low part of tank, and that could be quickly delivered to the room space for heating, only 20 minutes. Where traditional heat exchange tank need at least 3 or 4 hours. So which means in morning time, we can quickly use solar energy to provide heating rather than the buzzer heat pump. So this is a test result at 3 different days. Yeah, you can say it's a similar profile, quickly heated in 20 minutes, then delivered to heating. So this is our test and simulation. Look at the number demonstration profile. We got this technology widely demonstrated in different locations in China and also in the UK. This is a second panel installed in Shanxi province, city in Shanxi province. It's a village house. We got good performance. Actually, we got a total of 100 houses installed in these technologies. And this is a 5 kilowatt system installed in Guangdong 5-star Solar Limited. This is a 5 kilowatt system installed in the applied science building of University of Hull. So it recently established the prototype at the sponsorship of BERS. This is a 20 kilowatt system that is to be installed the whole city library, which is to be completed in the next 2 months' time. Currently, we got manufactured at the way we shortly install the 20 kilowatt system in whole city library. Additionally, we have signed an agreement with whole city council to demonstrate and install our technology into the council house of whole city. Initially, we intend to install technology in 2 council houses. Then we got wide spreading of technology in maybe more than 100 to 100 installation in whole city council house. So that's all from me, and thank you for your attention, and happy to ask any question.
So thank you very much, Xudong. Very, very interesting talk. So colleague, do you have any questions? Any question for Xudong, please? Can you hear me? Any questions for Xudong?
Well, could I ask, your store, is that actually a very large tank of water, or is it an underground storage chamber?
Let me ask your question. So this is a tank with 1.5 big cubic meter. This is a water tank. We have this tank separated into two parts. The low part got only 20 liters. We can quickly deliver heat. So we can quickly heat up this amount of heat. That's a 1 cubic meter, actually.
There are some people who are not muting, so I didn't quite hear that.
I think, can you hear me?
Yeah, there were some people who had a lot of background chatter, not muted. I didn't quite hear you.
Yeah, can you repeat Xudong, what you said, please?
Okay, so we got what tank, or we call it heat storage, which is cubic meter, normally 1 to 1.5 cubic meter. So this is a large, but our technology is to separate the tank into two parts. Low part, we got only 20 liters. That's why we can quickly heat up the fluid and deliver heat to room space. But we got a fluid alteration. During the morning, we got the 20 liters of fluid quickly heated, then delivered to room space. But when solar radiation rise and the heat demand of buildings reduced, we got flow direction changed. We got fluid travel across the up part of the tank, which is a heat storage tank. We got part of heat stored and the remaining heat being delivered. That is why we call it storage and heat exchanger. There's a dual function in the one tank.
Okay, thank you, Xudong. Yeah.
Thank you.
Thank you.
So, other question, please. Other question for Xudong?
Yes, we want to ask in the slide of solar panels array,
Yes.
there is a tube of microchannel
Yes.
and there is an air gap within a solar absorber plate from black room. Between them, there is a structure adhesion. Okay, in the next slide, it was a silicon. It was made from silicon. Why adhesion, not welding? Even the welding will increase the conductivity.
We got kind of mechanical lamination technology prevent use silicon. We got things laminated use high temperature pressure machine. We try to prevent use of silicon. We prevent use of silicon. Instead, we use high temperature mechanical pressure technology, have the microchannel tube bonded to the base plate, the absorber plate. We prevent use of silicon.
It will not affect on conductivity.
No. We have things fully bonded without use silicon.
Okay, thanks, Xudong. Anybody else, other questions or any comments?
Can I ask a question? Very simple one.
Please.
Sorry, I probably missed what you mentioned this earlier. Is it
Okay.
heat the water or heat the room air?
Actually, we heat water. Water is a heating medium. It's a heating carrier. They got water transferred to the room space for heating room. This is the water, but actually it's not pure water. We got glycol, of course, because if we use pure water, we got frozen. Yeah, we got glycol and water. This is a fluid, like the central heating system. We got water flow across the loop and provide heat to room space to heating air in the room. But actually, it's It's got a double loop, and the solar loop is a kind of fluid, and also got glycol and water. It's a second loop that is delivered to room space for heating. Use a traditional outflow coil or use radiate.